Hi, I am Dr. Amari and I'm going to perform experiment 6, which is the weak acid strong base titration. The purpose of performing titration today is different from the purpose of the experiments that you did in 1045. In 1045, you did titration using the same setup, burette, pipette, and indicator looking for endpoint of reaction. That was to find concentration of the acid or concentration of base using purely the indicator, phenolphthalein, and for strong, if we have like a strong base for titration, you could use phenolphthalein is one of the best one for the to be used as an acid-base indicator. Today, the experiments that we are doing has different purpose also. The purpose of the experiment today is, first of all, we are using pH meter because when you do titration, the pH of the solution is changing. Let me share the document for a minute with you. And the pH is going to change. You start with an acid and you add base, the pH is going to increase gradually, and then you will have a sharp increase in the pH. Then it would reach a plateau. When you have that turning point where the slope is changing and the midpoint of that big jump, in that case, let me show you right here. When you have a big jump, this is the point of equivalence. When you have the graph that is based on the volume versus change in pH, the volume of the base used versus change in pH, we see as the more base we are adding, the pH is increasing, and we have this sharp change or big jump in the pH. The equivalence point, it's at the middle of this line here, and or the turning curve when it's going up and then it's turning direction. So the midpoint, you have equivalence point. The volume at the equivalence point is the milliliters of base that added to that. Let's say if you get like 16, if you divide that by 2, you get 8, and at the 8 milliliter, you can find the pH also. The pH at 8 milliliter at equals, or pH and half a point of the equivalence, that's equal of the pKa. So you can find the pKa for a weak acid. So the purpose of the experiment, the methodology is the same, it's the titration. The device that you are using is the same, but the application is different. First of all, you are going to see the pH meter, the change in pH, and when you see those graphs in lecture, you understand what it means, that you start with the acid pH is low, keep adding base, the pH is going to increase, but you have a sharp point where it's changing from acidic solution to basic solution, and you have your equivalence point right there. The strong base that we are using today is sodium hydroxide. Sodium hydroxide is not very stable. It actually absorbs moisture, and the mass is not stable. So if I just measure the mass of the sodium hydroxide to make a solution, it doesn't give me a reliable number for the concentration. It's not accurate concentration. So I'm here preparing sodium hydroxide solution. First, I have to standardize the sodium hydroxide solution. To standardize, I'm using KHP, and KHP is not potassium, hydrogen, and phosphor. It's actually potassium, hydrogen, phthalate. This is the solid is more stable, so it can be actually used as a primary standard. So we can titrate the sodium hydroxide using the KHP in order to find exact concentration for KHP. So we find concentration for KHP, then we are going to use vinegar for the as the weak acid to titrate with our new standard, which our new standard is the new sodium hydroxide. We have standardized it already. And then we find the concentration. So to perform the experiment, I'm using the experimental procedure from my lab manual. So I'm going to stop sharing this document. I just wanted to show you the graph that was for the equivalence point and what does half equivalent means, which is you divide this volume by 2, whatever it is, you find it in the graph, and then you find corresponding pH, which is equal to the pKa. And then if you take the anti-log of pKa, you get the Ka value for your acid. So that's what we are trying to do today. Definition for pH, it will be covered in lecture. It will be covered by your professor if it's me or someone else, maybe like a mini lecture is held using Blackboard Collaborate about more of the expectation and what is the about the theory and calculation or extra information. Not needed because you have your lab manual that you have purchased from Vital Source and you are going to use it for the experiment. Make sure you read it. All the calculation is explained there, and it also purpose of the experiment, why you are doing this experiment. Okay, I'm going to stop sharing. I stopped sharing document. So I'm going to start with the procedure. Based on the procedure, first we have to make the sodium hydroxide solution. So I already started because I wanted to make sure that it is completely dissolved. So I measured 2 grams of sodium hydroxide solid dissolved in 500 milliliters of DI water. Now, and step 2, we're going to Erlenmeyer flask, clean, dry Erlenmeyer flask. We are going to measure KHP. I want to check, make sure what you have in your data sheet. So for the data sheet, you need the mass of empty Erlenmeyer flask. So I'm going to give you the mass for empty Erlenmeyer flask. Okay, mass for empty. Erlenmeyer. Okay, I'm going to use the scale, the balance here, and measure the mass, which is 130.901 equals 130.901, and this is for trial 1. Trial 1. Then we are going to add 0.7, so it would be 130.6 about. So the mass now, we need the mass of the mass for KHP plus the Erlenmeyer flask equals 131.686. 68. Okay, 686. This is for trial 1. We're going to fill out the burette. Going to fill out the burette with the sodium hydroxide solution. So my sodium hydroxide solution is prepared. The beaker for sodium hydroxide is labeled. Going to prepare the burette. To prepare burette, you need to wash it first with deionized water. So rinse with deionized water. Add some deionized water to make sure there is nothing in there. And I dispense that into a beaker that is called waste. So I'm going to rinse the burette with DI water first. I've washed it before. I'm just doing it again to make sure that you see it's necessary to clean your burette. Then add about 5 to 10 milliliters of sodium hydroxide. You add 5 to 10 milliliters of sodium hydroxide. Rotate it to make sure that the area of the burette, whole area of the burette has been washed and rinsed with the sodium hydroxide. Then dispense it again because that was just used for washing. Fill it up to, I can fill it up to 0 or a specific number, but it has to be a fixed number. I'm going to put it more than 0, more than 0, and get some of the okay. The meniscus should be at 0. Okay. So my initial burette reading, now I have the initial burette reading. Zero. We need to add 60 milliliters of DI water to dissolve. Okay, just following the procedure. 60 milliliters of the DI water. Indicator, going to add phenolphthalein for the indicator. Start adding sodium hydroxide. Leave a white sheet of paper to be able to see the color. Make sure that your data sheet is not missing anything. The final. Okay. Just want to make sure the meniscus is exactly at 0. At the beginning, I can add sodium hydroxide fast. I'm bringing the camera closer, so hopefully you see the color. The pink color appears in the center, and it disappears. See the pink color? It appears and then disappears. When I mix it, it disappears. Still is not too close to the endpoint of reaction. At one point, that pink color is going to appear and stays longer. That means we are closer to the endpoint of the reaction. At that point, I have to slow down. Okay, now I'm adding a drop at a time, so I don't get too dark of a pink color. A light pink color is desired color for titration when I'm using phenolphthalein. If I get dark color, purple color, that means I have added too much of the base. Okay, a light pink color, and you need the volume, 39 milliliters. Final burette reading. Final burette reading equals 39.00. That was for trial 1. We have to do at least 2 trials, and the third trial is optional. The third trial, we only do it if the 2 that we have done, they are not within the agreement of like 5%. So for trial 2, we are going to have to do the same experiment, repeat the experiment. So first, I'm going to refill. Usually when it's like group of students working here, I tell one person responsible for flask, one for burette, but now I have to talk to myself and say, get ready, get the burette ready and get the flask ready, everything ready. Okay. So I have my burette filled up, but it's not adjusted to 0.0 exactly. Measuring mass for flask. Different flask, and of course it's different mass. So this is 118.913 grams. Mass of the flask, okay. 119.680, 119.680 grams. This is the mass of KHP plus Erlenmeyer flask for trial 2. Going to add the 60 milliliters of water, deionized water. Also, few drops of phenolphthalein. We add it to the flask with the KHP. To store it, to make sure it dissolves, to adjust the volume exactly at 0. And I check it for the meniscus to be at 0, and if it's not, I just take drops out. Okay. Going to start at 5 instead of 0. So when everything looks exactly the same. Okay. Adding the base. Last time I used about 39, so I can really go to 30 milliliters or 35 milliliters because I used almost same amount, not exact same amount, almost same amount. So I can go fast to about 30, 35, then I have to slow down. Okay. I just want to make sure you can see I'm not blocking your view. Let me know when to stop. Okay. Color appeared with addition of 1 drop, so I can actually stop there. And the final reading is 44.0. 44.0. Okay, we are done with part A of the experiment. I'm going to clean up this station, get some deionized water, and move to second part of the experiment using the same base. So I would fill up the burette. To prepare for part B of the experiment is to fill up the burette first. with sodium hydroxide. And I need to pipette 40 milliliters of acetic acid into 100 milliliter beaker. So to pipette, I'm given only the 10 milliliter, so I have to pipette 4 times. Bring it here so we can pipette the. To use the pipette, you use it in 1045 already, but you insert the end of the pipette into the pipette pump. You always hold onto the glass so it doesn't break. To pull the liquid in, you wheel down the pipette pump. This design of the pipette pump, that's how it works. You wheel it down to pull the liquid in. To wheel up, you dispense it into the beaker. So 4 times. And each time I have to bring the solution into the mark or the index line. There is the index line here, the brown line, that if I fill up the pipette up to this point, it's going to give me exactly 10 milliliters. One, 2, three, and 4. So I have the 40 milliliter of acid or acetic acid, my weak acid. And I adjust this exactly at 0. Maybe I bring it to 10 so I can see it better. That's it. That's one. I use this for pH. It's a pH meter. It needs to be calibrated, especially if it hasn't been used for a while. It needs to be calibrated. So I'm going to use a buffer pH 7. The buffer with a pH 7 in order to calibrate our pH meter. This is a multimeter, so it can measure like millivolt, it can measure pH. We are trying to measure the pH, so I changed that by changing the mode. Like this is a millivolt, and then we have pH, so it has to stay in the pH. We place the cell inside the buffer. And we are going to press standard. So the machine knows we are dealing with the standard now. So now it reads the pH as a 7.01. That means that if I put another solution, is going to read the pH more accurately. Okay. I'm supposed to place the pH meter into the acetic acid and add the base and record the pH. Because it's heavy, it might tip the beaker over. So what I'm going to do, I'm going to just basically utilize this burette stand and hold it, put the weight on the burette stand so it doesn't. Maybe it's easier to become like this. Yes. Okay. Now we're going to measure the pH using pH meter and keep adding the sodium hydroxide, record the pH for every 0.5 milliliter. It's going to be a lot of numbers, but you need the numbers in order to plot your graph. You do have a data table with on the data sheet. You have a table that you're going to actually fill all this in. I'm going to add. I may not add the 29 milliliters. I'm going to stop after I have to first add, and I see the increase in pH. Then I see a big jump. When I say big jump, it would be like more than 1 unit of pH change. So if it goes from 6 to 8 or 7 to 9 or 8 to 10, whatever, then I will stop. After that, I continue with 4 more readings. So the recording, trying to see how it's going to make it easier for me for recording, but let's see. Part B. For part B, before adding anything, the pH is at 2.82, 0 milliliter. pH is 2.8. 0.5 milliliter. pH equals at the 0.5 and then the side. Have to add the base weight for it to stabilize, 2.99. One milliliter. pH is 3.10. Three point two three. Three point three four. 3.60. Four point five. Okay. Six milliliter. 11 milliliter pH equals 4.01. Okay, not much of a change. 4.06. Eight 8.5 milliliter pH equals 16. You would think that the numbers are going to increase faster. So nine point five, 27. Three. 1. Five. Okay. 4.33. 11 milliliter pH equals 4.41. 11.5 milliliters pH equals 4.48. 8. Corrections, 11.5 milliliter. pH is 4.45. 12 milliliters. pH equals 4.48. So make sure you correct it. Okay. Now 12.5. I'm just writing tablets ready so I don't forget the numbers. Equals 12.5 is 5.7 and 13 is 6.1. 13.5 7 4.67 for 13.5 and 14 milliliter. pH equals 4.73. 14.5 milliliter. pH equals 7.6 and 4. pH equals 4.91. And for 16 milliliters, pH equals 4.99. 17 milliliter pH equals 5.9. Five point 26 for 17.5, 18 milliliter pH equals 5.46. The increasing pH is getting a little bit more significant, so that's the hope that sometimes soon we will get a jump in pH. $18.5. 5.64, 19 milliliter pH equals 5.89, 19.5 milliliter pH equals, let's see, 6.80, 6.80. $20, 9.67. That's a big jump. 20.5 milliliter pH equals 10.28. 21 milliliter pH equals 10.63. 21.5 milliliter. Seven three. 22 milliliter pH equals 10.63. 8, 9. So after the big jump, we have 4 readings. I'm just going to do one more. One more, 22.5. So 22.5 milliliter. pH equals 10.99. So you see the shape of the graph. For a gradually increase, big jump, and then gradual increase. Because I'm adding more base, of course, is that there would be never decrease of pH. So it's a gradual increase, and then a big jump, and then gradual increase. And when you have that big jump, that's the equivalence point. So when you plot the graph, you can find the exact volume. From the graph, you find the pH at that point. You find it, and then you divide the volume in half in order to get the volume at half the equilibrium point, and find the pH. That pH equals to pKa. Then you are going to the Ka by taking anti-log. And you want to make sure you show your calculation. You use Excel for plotting the graph. You don't have to use the graph paper. Okay, experiment 6 is done. And I hope that you record your data and finish your data sheet, turn in as an assignment. If you have any questions, you could ask your professor, if it's me or anybody. I'm going to stop the recording. That's the end of experiment 7, and thank you.